convert it. Probably, I guess the hardest part is, just doing that polar work. Taking that XY region, graphing it out, because it'd be tough to convert that to polar without at least seeing a picture. You gotta at least draw the two-dimensional picture, but I'm trying to do this with avoiding the three-dimensional graphing as much as possible. And then that's pretty straightforward to evaluate. Integrate Z. That's going to give me, well, Z R cubed, which will give me R to the fourth when I plug in my limits. Did I skip too many steps there?
No.
Z R cubed, upper limits R, lower limits 0, so you end up with R to the fourth when you plug in R for Z. And then when you integrate R, that's going to be 1/5 R to the fifth. The only non-zero contribution comes from plugging in 3. And 3 to the fifth, that's big. That's 243. Well, big is relative. And then when you integrate this with respect to theta, keep in mind your theta limits are just 0 to pi. And since I have a constant there, what's it going to do?
243 pi.
Just multiply by pi. Not a volume, though. What this represents is, and this is kind of the weird thing about integration. I don't know if you've ever had this described to you about the integrals that you do in Calculus 2, but Dr. Martin Evans was a professor of mine at University of Alabama. And when you evaluate something like the jam. When you integrate some function on the interval from 3 to 9, and so 3 to 9, maybe this is x squared dx. Okay, we have the context of area under the curve and stuff like that. But what he sort of tied it in with is, if you think about the way a Riemann sum is defined, you start off defining these as really skinny rectangles that are delta x units thick at the x-axis, but then they don't stay rectangles. When you evaluate a Riemann sum, what happens to your delta x, or what happens to the thickness of your rectangles?
Approach 0.
They approach 0. Delta x approaches 0, essentially approaching a point value, which means you technically don't have a base anymore. So when things go infinitesimal like that or get really small, what he said is kind of think of this as summing up every output that function generates for every input you get between an input of 3 and an input of 9. And by every input, every continuous, rational, irrational, every real number between 3 and 9 plugged into this function, summed up, gives you the value of that integral. Same idea here. If you sum up every fourth dimensional output that this thing generates from that region in space, anybody know what that region would look like? This is its underlying region. Can you use that equation pair there to kind of help you see what the 3D region looks like?
Is it kind of like a quarter of a sphere?
No, because that's z equals root x squared plus y squared. If you go one page prior, it's a cone. So z, when z enters this region, z enters at z equals 0, the xy plane. Z exits at the top, at the cone. So you got an xy plane being the base, and then z goes through and exits through the cone, and then r goes from 0 to 3 for that half the circle underneath it.
It's
Kind of
under
hurts.
the cone cut in half.
Yeah, that's it. If you see something looks like this. Well, what the heck, I'll draw on paper.
So it's like a little shelf.
Yeah, you're on the positive side of the y-axis, so the cone would open up something like this, and then you project it down to the xy plane, and it has this circle underneath it. So it kind of looks something like this. It's all the points that are under the cone above that semicircle. So it's, from our side, it looks like half a hockey puck. But when you look on the top of it, you see the recess of the cone. You can see that convex curvature of it. So that's, if we take every x, y, z coordinate in this, plug it into that function, x squared plus y squared, our original integrand, sum up all the outputs, they add up to that. It's one of the most abstract things to envision, but I remember Dr. Evans telling me that, and it's just sort of stuck with me ever since I first heard it in 1990.
And it's not a volume.
Pardon?
It's not a volume.
It's not a volume. I mean, it's the capacity measure, I guess, for that particular dimension. You know, like when you integrate over an interval from 3 to 9 for a function like this, you're calculating base times height of all those Riemann rectangles. Okay. So in this case, in the case of a triple integral that has a function inside of it, the base area is dx, dy, dz, a three-dimensional base. And then I hate it when I do this. And then the height of your object is the function x squared plus y squared itself, the integrand. But see, that's the 3 dimensions. dx, dy, dz is 3 dimensions for the underlying region. And then when you multiply that by the function height, it's the 4th dimension. So if you want to call it a hypervolume or a 4th dimensional volume, you're welcome to. Yeah. May make some sense. It's just hard as heck to picture it. Okay. Let me put you to the test. Using a triple integral, set up the triple integral for the function. Now notice your integrand is originally just x. The differential dv, remember what that stands for?
It's volume.
It just means you're in 3D space. Your domain for this integral is 3D, dx, dy, dz, which will eventually convert to dz, d, d theta. Okay? So you're just integrating over 3D space. That's what dv stands for. Take a few minutes and see if you can convert this to a cylindrical triple integral over this region in space. The region is all the points that are between a cylinder of radius 9 and a cylinder of radius 2. So the origin's right here in the middle. Envision the z-axis coming through in the center there. So this is technically like a cylinder with a core cut out of the center. A 3 radius cylinder with a 2 radius cylinder cut out of it, hollow. And then the top of it is cut by that plane up there somewhere above the x-y plane. Okay? So see if you can just convert it to cylindrical. Using your z, bar, and theta limits. Now keep in mind, when you're converting to cylindrical, none of your integral limits, none of your integrand information should contain the variables x or y. Everything has to be completely translated in terms of the cylindrical r, theta, z coordinate system. I do that in Paint. Totally do. Every graphic you see on these documents is in Paint. Lamest software ever.
Do you know what
What'd you say?
I've designed T-shirts in Paint.
Really?
I like that because you got good T-shirts. Right?
Awesome.
Yeah.
I designed the T-Matic logo for this past year's T-Matic conference in Nashville. It was Tennessee Mathematical Association of Two-Year Colleges. Yeah, I have no idea what that acronym stood for. Sorry about that. But it was in Nashville, so I designed it based on a guitar. And instead of the strings, being like, regular guitar strings, I made them like different amplitude sine waves, and they loved it. And they made T-shirts and keychains and all sorts of stuff. So, yeah, it gave me an excellent on my evaluation from Nancy. So I'm like, cool. But I couldn't use it this year. Let's see what you got.
So for X, did it have the P and stuff in it?
No, this is cylindrical. We haven't got to the rho, the phi, and the theta yet. So this is still in terms of R's, thetas, and Z's. So you should have a triple integral in terms of R's, thetas, and Z. You might want to check. You can check your answer when you get one. Hesitant. I may have put you to the task too soon. Only seeing a couple of examples. This would be tough in spherical coordinates. Spherical coordinates with the rhos, the phis, and the thetas, they work best when you have spherical objects. cylindrical coordinates works best when you have circular objects in the XY plane, but if you have 3D spheres, that's when the spherical system works better.
I don't know what the
Let me see how far you've gotten.
I don't know if that's correct, but
That's tougher than it needs to be. Because you saw that for Z. It's already solved for Z. Those are right for R and theta. And what was your integrated? I think you might have missed it. The original integrated was just X. So we want to make a
yeah, I
conversion for
like
it
that.
too.
Okay,
So it's not really a volume problem. You have an actual proper integrand, a non-unit integrand in there. All right. The integrand, see, is the easy part. So the integrand in terms of x, y, z is just x. When you convert that to polar or convert that to cylindrical, it's the same as in polar. So x becomes r cosine theta. But don't forget the extra r. Yeah, so it's technically going to be an integrand of r squared cosine theta. Anybody get that? No, the integrand's okay. So now let's use this image here to develop our limits. In my opinion, if every single cylindrical integral you ever do is z, r, theta order, you're going to be as consistent as I've ever seen it. Because I always see the order for cylindrical to be z first, then r, then theta. Because, or just because of the way it's set up. See, z is still the vertical dimension that you've always been used to. So if I go through this solid, okay, I want to go in the z direction from anywhere in the base. Now the base, keep in mind, is this annulus, this region right here between these two cylinders. So if I draw a vertical line representing z's direction, z enters down here at the base in the xy plane. It goes vertically, and so it's parallel to the cylinders themselves, and then it exits at the top. No matter where I draw that vertical line, as long as it enters somewhere inside the object and exits at that plane, you're always going to enter at the xy plane and exit at the tilted plane. So z enters at 0, where you're on the xy plane. What'd you get for z's exit?
R cosine theta plus R sine theta plus 5.
That's it. All you need to do is make those polar conversions. Z would exit at x plus y plus 5, but just making the right replacements for r, for y, and for x. So it makes for a weird looking integral, or at least especially when you put these limits on the integral itself. Okay. And then when that's flattened to the xy plane, you're dealing with these concentric circles, the two-dimensional region between a circle of radius 2 and a circle of radius 3. So I'd like to think r and theta might be pretty obvious. 2 to 3 for your r, yeah? And then all the way around, so 0 to 2 pi for theta. So converting this rectangular triple integral into cylindrical, looks like a big involved mess, but I'll do theta on the end, r in the middle, and then z in all its robust integral limits. Sorry I'm writing sideways there, but just sort of accommodating the space. And then the integrand becomes r squared cosine theta with the implied order dz dr d theta. Because again, every cylindrical integral I've ever done or ever seen in a textbook of any sort has always been in the dr theta order. Are y'all okay? Are you okay with that? Learn to be okay with that. Because I mean, that's in some cases cylindrical is a lot easier. Or I mean, if you've got enough experience with polar, cylindrical is just adding z. You're just adding the z dimension to it. All the other conversion formulas, all the other rudiments of rectangular to polar are still there. You're just adding the z component. That's all it is. Okay. I got one more challenging problem I want to show you before we leave cylindrical. That's this one. Determine the volume of the core that's removed from a sphere of radius 2 by cutting through its center. So in other words, you've got this perfectly centered sphere of radius 2, and you have a drill that'll cut out the center core along its central axis and remove a cylindrical section of the center of the sphere of radius 1. So in other words, you've got a
That's a very practical question.
you get a sphere of radius 2. You want to cut through it. Let's see, try to find its center as best I can. Okay, like that. Okay, so there's our XY axes. This is a sphere of radius 2 out there in space. I want to cut through it with a cylinder of radius 1. So right here in the middle, we're cutting into the core of it with a cylinder of radius 1 and removing this, well, maybe kind of Vienna sausage sort of shape. Like that. And then we want the volume of that part that we're taking out. Okay? Not the napkin ring that's left over. Because once you remove the core, you got like a napkin ring on the outside, and then you have the little Vienna sausage that you're pulling out. Can you take some symmetry into advantage here? What's the ultimate thing about three-dimensional symmetry? If everything is symmetric with respect to the origin, the x-axis, the y-axis, the xy plane, the xz plane, the yz plane.
1/8.
1/8. Yeah, just do the first octant volume. Just focus on that chunk of the volume right there. And then multiply that volume by 8, and that'll, account for all the other octants that are out there.
Do you have to do an eighth? Can you just do half and then?
Yeah, you could do the upper half. What's the only difference between an eighth and cutting it in half like Nick is suggesting? What's the only variable in cylindrical that will be affected by that? Theta.
Yeah.
What I've got drawn here in blue is 0 to pi over 2 for theta. What you're suggesting is still 0 to 2 pi for theta, but
Maybe even one.
letting z go from 0 to the top up here where the sphere is. Okay?
Maybe even 1/4, so that we'd only have a pi.
1/4, but I go for the ultimate. Just multiply that 1/8 octants section times 8, and you can take advantage of the symmetry of the sphere and the cylindrical cut that you're making. So I wouldn't do an 8th, right? So I'm going to say times 8. So 8 times this triple integral of this region looks like this. That little blue shape. So sorry about the bad notation there, but that's what we're integrating over. The integrating would be 1 in x, y, z. So let's just see about what our cylindrical limits would be. If you slice through this shape in the z direction, the first thing z is going to hit is the xy plane. The last thing it's going to hit is what?
Square 4 minus r squared.
The sphere, yeah. So I'm being kind of purposefully generic first, just to make sure everyone can see the picture. Z would go from the xy plane to the sphere. Now, those are the specifics. Z goes from 0 to. Now remember, the problem here doesn't actually give the equation of a sphere of radius 2. So I'm making a tacit assumption. Do all of you know how to come up with the equation of a sphere of radius 2? Do you remember what the left-hand side of the equation is always going to be for spheres?
X squared plus y squared plus z squared.
X squared plus y squared plus z squared. Because if you think of spheres, a radius like the magnitude of a vector, then that point in space is, well, the x coordinate, the y coordinate, and the z coordinate squared all together to get that length. So any point on the sphere would be essentially like the magnitude, the squared magnitude of a vector that's pointing from the origin to the point of the sphere. So since this comes from the equation x squared plus y squared plus z squared equals 4, we're wanting the top hemisphere, or this little tiny, almost triangular chunk of that little bit of almost like a yarmulke at the top of the Vienna sausage up there. So we still want that to be the top of the sphere, that surface is provided by the sphere. So if I solve this for z, I've got to bring the x squared plus y squared over, subtract it from 4, but then think in terms of cylindrical. That becomes r squared plus z squared equals 4. So the top is going to be z equals the square root of 4 minus r squared. I do believe that's what you told me. What are your r limits going to be when you project the blue shape down to the xy plane?
0 to 1.
0 to 1, because that's the cutting cylinder. The cylinder that's cutting through the core of the sphere is a cylinder of radius 1, so that projects down there as a circle of radius 1. So r goes from 0 to 1, and theta, based on my 8th symmetry,
0 to pi root 2.
is just 0 to pi over 2. Yeah. You could also double, like Nick suggested, or quadruple, and just depends on which way you want to do it. If you decide to double, you want to commit to 0 to 2 pi, because you're just doing the top half and the bottom half. But based on the little tiny section I've done, from here to here, that's theta equals 0 to theta equals pi over 2. And now we got everything set up. Let's see if this is going to be messy when we integrate it. Your integrated here in x, y, z was 1, but remember, in cylindrical, it becomes 1r. So if I pair everything with its correct limits, need to integrate z first. Well, let me ask you this. Would you be upset? Oh, well, first off, another big thing I've forgotten. What have I forgotten?
Here the R.
The 8. Yeah, I forgot the 8 times the volumes we need there, so don't forget the 8 because of the symmetry that I'm imposing on this. Would you be terribly upset if in my next step I just wrote it this way? Or have I made a mistake?
I will stand for it.
You see what I did?
Yeah, because you just multiply the
Okay,
final one by
No dependence on theta here whatsoever, so technically I integrated with respect to theta as the number 1. And so, you know, my top limit for theta is pi over 2, my bottom limit is 0, so it would essentially just give me that constant pi over 2 multiple like that. And anytime you see that in polar or in cylindrical, you see no dependence on theta in here, no theta variable inside here. You can automatically just, you know, apply that top limit as like a coefficient, okay, and then focus on your r and your z. Z is also easy because when I integrate z, I'm just going to get rz, which is, oops, lost my r. Your top limit for z plugged in, your bottom limit for z plugged in. I forgot to write them here. So you get this. And then when I integrate this with respect to r, okay. Anybody need to go through the U sub just to make sure? Yeah, why not? Okay. What's your commitment for u?
4 minus R squared.
4 minus r squared. Always go for the quantity and the grouping. Oh, and don't forget this. There's technically a 4 pi on the outside of this from the 8 times pi over 2. So start with all the lines here. Let u equal 4 minus r squared. Du gets replaced, or will replace, negative 2r dr. So, I'm going to fudge my negative 2 that I need in here already and just divide it out. It's probably the simplest thing to do. And then you kind of freak out because you're getting a negative compensator from your U sub, and this is originally described as a volume problem, but don't worry, it should be okay when we're done. The correct order of integration should make things work out right. My integral here will be u to the 1/2 du. The original r limits are 0 to 1. I'm sorry, y'all, I'm changing my limits. Lower limit for r equals 0, becomes a lower limit for u as 4. Come on, try it out.
Okay,
You might
yeah,
enjoy
what's
it.
up?
Make t-shirts. The upper limit for r equals 1
Three.
becomes the upper limit of u equals 3. Okay? And so, well, there you go.
That changed.
Yeah, if you're always accustomed to seeing your integration order from least to greatest here, and if you flip that, there's how you can get rid of the negative if you want to. So it should be a positive answer when you're done. Do you remember that property of integrals that says you can reverse the limits, and then that causes a sign change in the front? You probably have never used that since the first day you saw it. But here's a case where you can use it. It's kind of cool to bring up little things like that. When you see they're kind of practical. All they do is just flip the limits, and that causes a sign change. So then, finally, getting this volume. U to the 3/2 with a 2/3 coefficient. So we're going to get an irrational answer, but that was expected. When you deal with parts of spheres, usually some irrational numbers show up, and not only pi, but other things too. So I've got 4 pi over 3. Let me give myself some room for this. Times 4 works okay with the 3/2 exponent. Square root of 4 is 2. 2 to the 3rd is 8. But then 3, unfortunately, I'm just going to leave as 3 to the 3/2. You're welcome to write that as 3 square root of 3 if you want to. That's another way you can equate that. But that value that value does, I'm pretty confident, that represents the volume of the Vienna sausage core that we've removed from that sphere of radius 2. And if you've never had a Vienna sausage, now you have an excuse to go see what they look like. They look like cylinders with little tiny spherical caps on the end of them because they pump when they get full. Anyway.
They pump when you cook.
And now that's ballpark winners, yeah. That's a whole different winner. Okay.
That's good.
Any questions so far?
Yeah, will you get a job at UT so you can be my math professor next semester?
I love the teaching. I've never been a fan of research. I did a little bit of research as a grad student. I just love the student interaction. I love drawing the pictures, and I love making relatively complex kind of ideas seem attainable and understandable. Because I tend to teach things the way I wish it would have been taught to me, just because I just love this stuff. And so, I'm sorry though, I'm going to stay here for Mississippi.
Oh no, I didn't mean you.
This is my 15th year. I got the employee awards day today. I got $50 for being here for 15 years. So yeah,
Whoa.
they really like me. All right. Shall I show you spherical?
That's just a section that's missing from the sphere?
Pardon?
That's just a section that we took out of the sphere?
Yes. This is based on these limits. R goes from 0 to 1, and well, strictly based on the R limits only. Just based on those R limits, that dictates the fact that we found the core that was removed. Good question. What if you want the volume of the napkin ring that's on the outside of the cylinder? What's the only thing that would change here?
R.
R. Z would still need to go, if we're still using the same symmetry, we're now going to try to find from here outward across to here, up to the top of the sphere. Okay? And then multiply that by 8. So Z would still need to go from the XY plane, because I'm still going to do the 1/8 symmetry thing. Z would go from the XY plane to the sphere on top. Nothing would change here. R would now need to go from the inner radius 1 from what you're cutting and removing, and out to the outer radius of the sphere, which is 2. So that would just change from 1 to 2. That's it. That would still be the first octave chunk, and then multiply by 8 at the end. So the only thing that would change is just R would go from 1 to 2. If you wanted the napkin ring volume instead of the Vienna sausage volume. Okay.
All right, can you slide that back up into the last?
Oh, the final answer
Yeah.
was that. Your back row need to go higher than that. But you're a tall fella, you can see it. Did you not get that?
Got it. -4/3, or -4 pi over 3 times the square root of 27.
Okay, that's what this is. This will be the square root of 27. Because that half means square root, and 3 cubed is 27, so there's square root of 27. Did you forget your lower limit? If you undid u at the end, back to where it was the root 4 minus r squared,
Yeah.
be careful. When you plug in r equals 0, that doesn't vanish. You're taking the square root of 4 minus 0, so
Yeah.
there's going to be a non-zero contribution from that limit. Okay. And that order of subtraction in here is a negative number times the negative you have in the front. So you're essentially doing negative times negative, you get a positive volume.
I'm terrible at always assuming if I have a zero, I just.
It's eaten up a lot of points for a handful of calc students over the years, assuming that zero lower limit wipes everything out. So yeah, if you had left your R expression as root 4 minus R squared, when you plug in R equals 0, which was the original R limit, for the lower limit, that gives you a 2. So beware. So the spherical coordinate system. Okay, I've got a picture here that, in all honesty, I mean, I've been using this picture for years since I first made this document, but this is kind of a lame description of the way the spherical coordinate system works. A couple of analogies I can draw to sort of help you envision the spherical coordinate system. You have 3 variables that locate points in the spherical space. Still 3D space, just like x, y, z. You have the variable rho, looks like a Greek P, perhaps rho. You have the variable theta, which is the same polar theta. It sort of exists in the xy plane, and then, you know, from 0 to pi over 2 to pi, same theta as always. But then you have this third angle, phi, or phi, however you're going to pronounce it. And it represents the tilt off the z-axis, okay? So one analogy I try to draw with this picture is if you imagine locating points in 3 space like using a joystick from old 80s video games, okay? Like if the length of the joystick represents the rho value. Rho you need to kind of think of as the radius of a sphere. Rho is not like R. R is sort of stuck in the xy plane dimension. It only goes from 0 outward, you know, parallel to the xy plane. Rho goes out in all directions like the little rubbery parts of a koosh ball or like the explosion of a firework, you know. Rho goes in all directions, 3 dimensions all the way around. So that's the way rho works. Rho goes from the origin outward omnidirectionally.
3-dimensional R.
3-dimensional R, yeah. Where R is just sort of flat. I mean, R can be up here, you know, but it's still locating, you know, R values this way. Rho goes in all directions, okay? So if you think of the length of the joystick, going back to my joystick analogy, the length of the joystick is like your rho. And we can have the joystick going in any direction, but we can tilt the joystick off of its vertical. When you let go of the joystick, it sort of spring loads back to due vertical, like the z-axis, okay? And then if you grab the top of the joystick and tilt it, that tilt that you apply to it in any direction is the value of phi, okay? And then if you tilt it forward and then you want to rotate it this way, after you've tilted it, that rotation is the angle theta. So if I could create a 3-dimensional like graph paper for the spherical coordinate system, well, actually it's already been created. Anytime you look at a globe, you've got, you know, the rudiments of the spherical coordinate system looking at you. If I just draw the first octant chunk of what it would look like. Okay, so that would represent, let's say that's a rho value of rho equals 6. So that's essentially 1/8 of a sphere of radius 6 in all directions. So any point from the origin out to the surface of that sphere represents a constant value of rho equals 6. Because rho goes in all directions. So rho is pretty much like a sphere's radius, where r is like a circle's radius, you see. And then if I consider different phi values, phi is almost, well, no, not almost, phi is exactly the same thing as levels of latitude on a globe. See, if you draw little lines like this that represent equal pitches off of the z-axis, well, as best as I can freehand, like maybe from here to here, that's phi.